Um, we're finishing up on chapter 7. We're taking a lot of time on kinetics, but it's pretty interesting stuff, so I figured that it's okay. When last we met, I'm just going to, I think, copy the figures because rather than try to reproduce it all. Did I not copy? This is embarrassing. Copy. Paste. All right, good enough. So we've been talking about these Moore, O'Farrell-Jenks diagrams. We've been thinking about reaction coordinates. We reasoned our way through the SN1 and SN2 reactions by thinking about how changes in the potential energy surface might change the mechanism of reaction. You'll recall that the y-axis here was the distance between the nucleophile and the carbon of the alkyl whatever, halide or something. Here is the distance between the carbon and the leaving group, and a perfect SN2 reaction would just go straight down the diagonal. Leaving group leaves as nucleophile comes in. However, we notice that as you start to change the structure of the carbocationic intermediate, you start to make the SN1 reaction more accessible. Here is a case where you've gone from methyl to primary to secondary to now tertiary alkyl halide. We've noticed that that lowering the energy of this carbocationic intermediate does a couple of things. First, as we get to the tertiary alkyl halide and even the secondary alkyl halide, it makes the rate of that SN1 step comparable to the rate of the SN2 step. But the other interesting thing it does is it tends to pull the SN1 transition state away from being completely, I would say, synchronous, meaning the leaving group and the nucleophile are leaving at the same, are coming in and leaving respectively at the same time, and starts to pull that transition state towards one part of the reaction coordinate. So, and this is more obvious if you look down on the molecule from above. As we lower the energy of this sort of lower left-hand corner by making the carbocation more stable, we start to tip the location of the transition state towards a little bit less nucleophile coming in and a little bit more leaving group left. So that by the time you get to the tertiary alkyl halide, if there were even going to be an SN2 transition state, it would have to be pretty carbocation-like before the nucleophile even came in. So this is often an effective way of plotting or thinking about reaction mechanisms. And one of the things that we will see if you're considering a reaction mechanism like this, you can think about making changes to the potential energy landscape and make some pretty good predictions of what those changes will do to the transition state. So if, for example, you make changes at these points that are off the diagonal, these two corners, if you were to stabilize the lower left-hand corner, I'll put a down arrow there, meaning we're pushing the potential energy surface down in that direction. That will pull the transition state in a direction perpendicular to the diagonal, which I don't know if that has a theoretical basis or if that's just topology of surfaces or whether that's just an empirical observation. But that's what we see for the SN2 reaction. As we stabilize this lower left-hand corner, the transition state moves perpendicular to the diagonal. Similarly, if we were to stabilize the upper right-hand corner, we'd move in that direction. If we were to destabilize the upper right-hand corner, we would also move in this direction. Sort of Make sense? Okay. Another way you can think about these diagrams is to think about what happens when, and this is maybe a little bit counterintuitive, what happens when you start making changes along the diagonal at the two corners that correspond to the reaction coordinate. So here you can no longer think of it like you would a marble rolling around on a sheet, and you raise one end and it goes this way, you lower this end and it goes that way. Here you have to think of the Hammond Postulate. Okay? So imagine I raise the energy of the right-hand corner up. See, I get left and right wrong. Oh my gosh. Imagine I raise, this is my right hand, I can tell because I have a pen in it, and I'm right-handed, so this is my left hand. Thank you for bearing with me through all of that. Raise the right-hand corner. Ah! Did it again. Left hand. Okay, Joshua, we're raising the energy of the left-hand corner. That's destabilizing the starting material, and that should bring the starting material closer in energy to the transition state, which means the transition state is going to start looking a lot more like starting material. So when you start to make changes at the corners that correspond to the diagonal, you start to get what are called Hammond effects. That is, if we raise the energy of the starting materials, our transition state gets more starting material-like. All right? In contrast, like we just discussed above, if we raise the free energy of this corner, we're not going to move the energy toward that corner. We're going to move it this way. And they call that an I don't know what the other dot is, an anti-Hammond effect. But I don't know that you need to think of it that way. Just think of making changes off the diagonal as just having the logical effect you would expect for like having a marble rolling around on a surface, and you raise one side and the marble rolls away. Similarly, if we stabilize the transition state, stabilize the starting material, that's going to make the starting material farther away in energy from the transition state, and so the transition state will be less starting material like, and it will be later, and so it's going to move the transition state forward along the reaction coordinate. And this is just, why do you care? This is just how people talk about kinetics. So I want to show you an example where this matters and where you can use this kind of analysis to rationalize some experimental results. So I'm going to crop this so we're only worried about the right stuff at the right time. This image is showing you a proposed mechanism for phosphoester hydrolysis. All right, here is a phosphoester. Oops, I guess I'm going to need a smaller point. And the uncatalyzed reaction basically involves an SN2 type mechanism where, as we talked about, you've got a leaving group here, and then you have a nucleophile here, and the reaction is going to involve a transition state where there's some amount of leaving group leaving and some amount of nucleophile coming in. And one of the things that they observed was that in this uncatalyzed reaction, the transition state involved, let's see what they said, about 37% attack of hydroxide. I believe that's how they interpreted it. Okay? So that, wait, sorry, I think I got that wrong. So at the transition state, the leaving group was 37% gone, and there was substantial bond formation between the OH and the phosphorus. And if you think about this reaction, like we've talked about before, you've got two reaction coordinates. You've got the distance between the phosphorus and the leaving group, and then you have distance between phosphorus and the nucleophile. So they figured this number out through some kinetic experiments that we don't need to know. But then they were studying a catalyst that promotes this reaction and accelerates it. And we're not going to talk about why the catalyst accelerates the reaction or why the catalyst is different, but we do want to rationalize a result that came from the catalytic study. And what they found was that if you use the catalyst, now the transition state involves the leaving group being now like 77% gone. And this is troubling because they anticipated that the nucleophile on the catalyst was better than OH minus. And if your nucleophile is more reactive, you would assume that it doesn't wait around for the leaving group to leave, but instead comes in and attacks earlier. Notice that in the catalyzed reaction, it's a little bit different. The rate determining step involves the leaving group leaving, and now our nucleophile is not hydroxide, but it's this this bridging cobalt oxide. And it's not showing you yet how it's not showing you the OH group coming in, presumably in this step, and I'm not sure which oxygen it would be, but you need an OH group to come in and then get deprotonated to displace the oxide. And then you've hydrolyzed your phosphoester, okay? So they wanted to know, how could this be going on? The catalyst somehow makes the leaving group leave even more than it had left in the uncatalyzed reaction. And again, that's troublesome because they've anticipated the nucleophile would be even better. So they rationalized this with one of these more O'Farrell-Jenks plots. Here you've got you've got phosphorus nucleophile distance. Here you've got phosphorus leaving group distance. Here you have starting materials, and here you have product. And this is kind of backwards from what we did above. Above we had starting material in the upper left and products in the lower right. Now we're starting with starting material in the lower left and products in the upper right. Here is the starting material is phosphoester bound to catalyst. The product is the leaving group has left, and you now have the hydrolyzed phosphate group still attached to the catalyst. Up on the upper left-hand corner, you have nucleophile attack, but leaving group still there. In contrast, in the lower right-hand corner, you have leaving group gone, but nucleophile not having attacked yet. All right. And of course, the pure sort of synchronous SN2 reaction would have been this straight line. All right. And what they're showing you with this dot is, and I don't know what color we'll make it, maybe pink for uncatalyzed. The dot represents the transition state of the uncatalyzed reaction. And what they are proposing, whereas the blue dot is going to represent the transition state of the catalyzed reaction, blue for cobalt, I guess. And what they proposed is that formation of this bond between the nucleophile and phosphate generates two strained four-membered rings. Let's highlight those. There's one, and there's another. And that is present on the whole edge, on the whole top edge of this potential energy surface. Okay? So they propose that what those strained four-membered rings do is destabilize the upper edge of this potential energy landscape. And so now we can analyze what that does to the transition state. Remember, along the diagonal, if we destabilize the product, that means that the transition state has to get more product-like, right? So that explains why we're moving in this direction, and this is the Hammond effect. In contrast, if we destabilize this corner, I don't know, there's no rhyme or reason to the color I'm using. I'm just trying to make it different. If we destabilize that corner, that's where we get an anti-Hammond effect. That's going to, as we lift this upper left-hand corner, the transition state is going to tend to roll away from that upper left-hand corner perpendicular to it. And you add both of those sort of changes together, and you get the movement of the transition state sort of by vector addition all the way to here. So you can actually learn a lot from this, these kinds of experiments and analysis as to how catalysts work, which is one of the most important and interesting areas of organic chemistry. We've got a catalyst, it makes the reaction go faster. How does it work? Why does it work? And can we make stuff that's even better? And in this case, the answer appears to be the catalyst works because it's got a nucleophile that can generate a strained four-membered ring, and that pushes the transition state even further down the reaction coordinate. Now, in terms of the relative energetics and this reaction versus the uncatalyzed reaction, they're not talking about that here. You could go look up the paper and your book references it. All right. Any questions you want to ask? Yeah, Mario. Oh, how would you make this graphic? Yeah, they're not showing you where the data are coming from. It's a good question. My guess is it's calculations, but based on data. I think they got this information from data. I don't know. It's a great question. Yeah. Yeah. So along the sort of regular reaction coordinate, along the line from starting material to product, the Hammond postulate dominates. So somewhat counterintuitively, if you're going to raise the energy of the starting material, necessarily the transition state moves closer to the starting material. All right? But perpendicular to that reaction coordinate, basic potential energy principles apply, and that is if I move this corner upwards, the transition state's going to move away from that to take a lower energy pathway. I don't know the fundamental difference why that's the case, But as long as you remember along the diagonal, I'm going to think about the Hammond postulate. Perpendicular to the diagonal, I'm just going to think about a little marble rolling around on a sheet, and the effects are going to follow that. Is that okay? All right. Cool. What else? The next thing we're going to talk about for potential energy surfaces is going to lead us right into Chapter 8. So, yeah, we'll insert that one. And this is something that I didn't really appreciate. There's a lot of things I didn't know till I started teaching this class. So here is a sort of lowest energy trajectory from one potential energy minimum to another. Why is it not letting me draw? All right, this might be our SN2 reaction. Here's a well for our starting materials. Here's a well for our products. But one of the things that your text points out is that perpendicular to the reaction coordinate, you actually have these individual energy wells at each position along the reaction coordinate. And this can represent a vibrational energy well, or the molecule at each state along this trajectory can occupy these wells at various vibrational energy levels. Okay. Remember that each position along the reaction coordinate represents a certain geometry. And we're changing in a certain direction to convert starting material into products, but there are other motions along that reaction coordinate that don't involve conversion of starting material to product and instead involve variation in some other direction. And we can think of that as being other vibrational degrees of freedom in the molecule. I'm not sure I've explained that very well. Ask me some questions and see if we can get at a better understanding. Go ahead.
So there are ways that the starting material can become the reaction coordinate that lead to it just going back to starting material?
Well, sure. I guess you've got, usually along a reaction coordinate, you've got vibration in one direction that leads you more from starting material to products or back from products to starting material. And then there are other vibrational modes that don't do anything to that change. So think of it as I'm just going to make this up and hopefully it won't be wrong or too inaccurate, but think of an SN1 reaction. It's vibration here that's going to make the leaving group leave, and not necessarily vibration or stretching of the CH bonds.
So those can serve the starting material that
Sorry, say that again?
With those vibrations, then the CH bond just stretches and comes back and makes the change.
That's right.
Molecule.
That's right. And so in this example, and I'm not sure if we're thinking about it correctly, and we could even make this an SN2 reaction and think about a nucleophile coming in. But it would be the vibration along this bond between carbon and leaving group that's going to carry you in the direction of the reaction coordinate. And then other stretches, wags, and vibrations are going to be, will cause energy changes, but they're going to be along directions that are orthogonal to the reaction coordinate. And these are going to basically represent internal but non-productive, I guess, degrees of freedom that are not involved directly in the reaction. And these energy levels are quantized, and it turns out the shape of these sort of instantaneous valleys can actually influence the reaction and can represent something that, frankly, the potential energy surface has not represented so far. When we've thought about this y-axis, we've thought about energy, which we've basically interpreted as free energy, but mostly enthalpy, because that's the one we know about when it comes to bond making and bond breaking. Instead, we're going to look at the shape of these, we'll call them perpendicular valleys, because they're perpendicular to the reaction coordinate. The shape of these perpendicular valleys is going to be related to entropy. If a valley is wider, as is the case here, right? The valley at the transition state in B is wider than the valley for the transition state in A. That means the transition state has more degrees of freedom. Wider perpendicular valley means more degrees of freedom, which ultimately means more entropy. And one of the ways you can tell that that's the case is because at this transition state, we can vibrate and move other geometries in either direction here without changing the energy very much. And so that means more vibrational motion is tolerated at that transition state that has the wider perpendicular valley than one that is narrow. In particular, the difference in the shape of the valley at the starting material and the transition state can be informative. So in C, you kind of see a broad valley here, but at the transition state, it narrows, okay? Broad perpendicular valley at starting material would indicate large number of degrees of freedom. Narrower valley at the transition state would mean fewer degrees of freedom. So what would that tell you? I don't know why I'm writing in purple. I just haven't bothered to change it. What would that tell you about the activation entropy? It would decrease going from starting material to transition state, because before you had a lot of latitude to vibrate, then you get up to the transition state and you have less freedom. Your text uses a kind of silly analogy about driving cattle through a mountain pass, and how even though if you had, imagine multiple pathways through this mountain, imagine one going off in another direction that is higher in energy but is a broader valley. It might be faster under certain circumstances if you're trying to avoid cattle rustlers, and this is where the explanation just went off the rails. But there might be a situation in which even if this is the lower energy pathway, the pass is too narrow to get through rapidly, and so at certain temperatures and with certain other shaped valleys, it might be actually better to go over the broader valley. Okay, this is all sort of hand waving, but it gives you a reference for sort of how potential energy surfaces can influence the course of a reaction. Go ahead.
Even though that path would require you to run your cattle up a steep slope, it's still better than the narrow pass?
It might be better than a narrower pass, yeah. I'm trying to, because broad is the gate and wide is the gate and broad is the way that leadeth unto the deaths, and many there be that go thereat. Whereas straight is the way and narrow the gate. I don't know. We're talking about these vibrational energy wells at transition states because that's going to be a key portion of what we're going to do in Chapter 8. when it comes to talking about kinetic isotope effects. All right, so that closes chapter 7. We're glad to put that one to bed. In chapter 8, we're going to discuss classic kinetics experiments that tell us which bonds have been broken, formed, or which carbons have been rehybridized in the transition state. Because typically rate experiments, though they tell you what things are involved in the rate determining step, they may not tell you exactly which bonds are formed in the transition state and to what extent. They may not tell you which carbons are rehybridizing. And in simple reactions, you can sort of reason your way through that. But it's useful to have experiments that can give you insight into exactly what is changing at the transition state. So the one we're going to spend a lot of time on is called kinetic isotope effects. And the concept here is fairly simple. The concept is that we're going to think about bonds and bond vibration as springs. And we're going to remind ourselves that deuterium is heavier, if we can spell, heavier than hydrogen by a factor of 2, right? It's sort of 2 to 1 in mass. Because, of course, deuterium has an extra neutron, whereas the hydrogen has none. Okay, and we need to rationalize what this does to bond vibrations. And to do this, we need to remind ourselves a little bit about bond vibrations, and maybe you know this from P-Chem. I certainly didn't, because I didn't have to take the kind of P-Chem that requires you to know this stuff. So, new for me. This is a potential energy well. It's called a Morse potential diagram, but along this axis you've got energy, and along this axis you've got bond length. And this could be a CH bond or an HH bond. We won't worry about precisely what kind of bond it is. We'll be general at this stage. All right. And there are various vibrational levels that can occupy this potential well. By the time you get up here, you've got total dissociation, or in this case, for this diagram, it would be sort of homolytic bond cleavage. By the time you are able to vibrate far enough to get over this barrier, then you can go to infinity, basically, and the energy doesn't change as much. All right? And these energy levels are quantized. We call them quantized vibrational modes. And understand, I'm only showing you the vibrational modes that apply to vibration along this bond length. Okay? There are other vibrational nodes in the molecule, but we're just talking about a specific bond. Those energy levels are equal to n plus 1/2 times Planck's constant times the frequency of vibration, where n equals an integer starting with 0. Fascinatingly, this means even at the lowest energy vibrational state, great, the Apple Pencil battery is low. Even at the lowest energy vibrational state, you still have vibrational energy. You can't get to the bottom of the well. It's inaccessible. The lowest possible energy you can have is 1/2 times Planck's constant times the frequency. Okay? We call this the 0 point energy, and it means that bonds are always vibrating. Frequency can never equal 0. Kind of cool. Atoms can't be motionless. All right. So what does this mean specifically for us in our kinetics experiments? Well, if you model a bond as stretching of a spring with mass on either end, suddenly you're in the classical physics area, and that vibration should equal 1 over 2 pi times the square root of k, which is the force constant for the spring. Bigger k means faster bond vibrations, right? K is associated with stronger bonds, so it's force constant. Increase k equals stronger bonds, which equals higher frequencies. And then in the denominator is this thing called reduced mass. And I'm not sure where the derivation for reduced mass comes from, but it is equal to mass of the thing on one side of the spring times mass of the thing on the other side of the spring, all divided by the sum of the two masses. I guess this assumes that the spring is massless, which in our case it can be. All right. So let's think about how this expression changes our understanding. Let's think about a bond where we would have maybe a CH bond versus a carbon deuterium bond. And we're going to think about the 0-point energy level. Okay? So for a bond between carbon and hydrogen, the mass 1 we're going to say is 12, mass 2 is the proton going to equal 1. And we're going to let n in our expression be 0. So E equals 1/2 Planck's constant times nu. The frequency, and nu is going to be equal to 1 divided by 2 pi times the square root of k over, and then the reduced mass. And just bear with me for a minute. I know you hate math, but this is going to show you where kinetic isotope effects come from. The reduced mass for carbon and proton is actually going to be 12/13 or 0.92. So I'm just going to do 12 over 13 here because it bothers me to write decimals that are only approximations. I'm sorry. Now let's do the situation where we've got a CD bond. So M1 is equal to 12, M2 is equal to 2. So energy equals 1/2 h times nu, where nu equals 1 over 2 pi divided by k divided by, and now mr for this new situation, I've already run the numbers so you don't need to worry about it, is actually 24 divided by 14, or approximately 1.7-ish. So if you want to, you can calculate, based on these assumptions, the difference in vibrational energy for the CD bond versus the CH bond. And okay. And we could come up with a number for that based on the numbers we've calculated so far. And what we would find is that the 0-point energy for the CD bond is lower than the 0-point energy for the CH bond. that follows in a pretty straightforward way from our calculations. Notice these frequencies, assuming the force constant's the same, we got a bigger denominator here than we do here. So the vibrational frequency for the CD bond should be lower. Yes. The vibrational frequency for the CD bond should be lower in energy than the vibrational frequency for the CH bond. So that puts the 0 point energy for a CD bond lower down our potential well than the 0 point energy for a CH bond. Okay? Now, let's talk about how that influences bond strength, shall we? And let's think of it in terms of both thermodynamics and kinetics. If you wanted to break the CH bond, and suppose that breaking the CH bond in this case means homolytic bond cleaving, then the energy you have to do is to go from this point all the way up the Morse potential. And we're going to pretend that homolytic, the fully cleaved sort of C radical and H radical is our transition state. Now that's unrealistic because in most transition states the bonds aren't completely broken. But then we would call this energy difference in purple the activation energy for the CH bond. And then let's say in orange, in order to get to the same point, we've got to start out lower in the well. So this is our energy activation for the CD bond breaking. And so what we would observe is the energy of activation for the CD bond is actually higher than, the energy of activation for the CH bond. Okay? It takes more energy to get out of the potential well if you're deuterium, if you've got a C carbon-deuterium bond, than for a carbon-hydrogen bond. And that's because the carbon-deuterium bond starts out lower. And we can actually measure that energy difference. In fact, it's not hard to calculate. The difference in activation energy is going to be equal to activation energy for the CH bond minus activation energy. Oh, sorry, we're starting with CD. Sorry. CD bond minus the activation energy for the CH bond. But that's also equal to the difference in 0 point energy for the CH bond minus the 0 point energy for the CD bond. In other words, orange here minus purple is the same thing as this distance, which I'm highlighting in blue. Okay? So let's talk about how that affects reaction rate. Bond breaking for a CH bond should be faster or slower than bond breaking for a CD bond. Faster, right? Faster by an amount that relates to this energy difference. Okay? Now, if you remember from chapter 7, when we talked about rates, we said we had a sort of Arrhenius expression for rates, and we said that the rate constant for a reaction was related to some pre-exponential factor times the number E raised to the, and I'm just going to write exponential to represent number E, raised to the activation energy divided by RT. And that's if you want kilocalories per mole. If you just want kilocalories per molecule, you use Boltzmann constant, Kb. All right, so the rate constant for hydrogen should be equal to some pre-exponential factor and I'm sorry, it's a minus thing because the larger the energy, the slower the reaction rate is. Activation energy for a CH bond divided by Boltzmann's constant times temperature. Similarly, the rate constant for breaking the carbon-deuterium bond ought to be equal to the opposite of the activation energy for the carbon-deuterium bond breaking divided by Kb times T. And then if we wanted to divide the rates to determine whether hydrogen's faster than deuterium, what would come out of that analysis is it all depends on the difference in energy of activation for deuterium versus hydrogen. Okay, and if you run the numbers for based on this assumption that you're going to go from the bottom of a potential energy well to a transition state that's all the way up here at the top, and if you make some assumptions about what the basic bond vibration is for a carbon-hydrogen bond, you would see that the number comes out to be about 7. So for a process where a CH bond is completely broken in the transition state, we can expect sort of a maximum kinetic isotope effect, that is a maximum rate of the reaction for hydrogen versus deuterium of about 7. Your book says 6.5, 7 is easier to remember. Okay? And that's all based on the fact that heavier springs vibrate slower and with lower energy. Okay? So if you observe this kind of effect, so what do? You do an experiment, you make the molecule where you think a bond is breaking, you put a hydrogen, if the hydrogen's involved, and this is typically the kinetic isotope effects are bigger with hydrogen because the relative difference between hydrogen and deuterium is bigger, say, than the difference between carbon-12 and carbon-13. But you figure out what bond you think is changing in the reaction. If it's a CH bond, you try the reaction with CH and you measure the rate. Then you try the reaction with deuterium at that carbon and you measure the rate there. You calculate rate constants like we learned how to do in Chapter 7, and then you compare them. All right? If the ratio of those rate constants is high, like around 7 or some value that's greater than 1, you might conclude that breaking of that bond is somehow part of the transition state. Alternatively, you might observe that the ratio of the rate constants for hydrogen versus deuterium is 1, in which case you might conclude that bond isn't broken in the transition state. But it gets more complicated than that. What we're really asking is, what we can observe will depend on what the transition state is. For example, if the transition state has about the same difference in 0-point energy for hydrogen and deuterium as does the starting materials, you may not see as much of a kinetic isotope effect. So we'll talk about those complexities later, but it's important that you understand where this comes from and that you understand that the maximum effect you're going to see is an acceleration in rate of about 7. All right, that's as well as I currently understand it. I'm going to hit the books and be better prepared for you on Wednesday. So that will end our discussion today.